In this video, we're going to discuss what seems to me to be my students' absolute favorite topic, which is applications, but otherwise known as story problems. And I say that with a smile because students come into this topic usually with having had bad experiences with it in the past. They're not happy about it. They'd rather just solve some straight equations. But really, life is a story problem, and so you really need to do these. And once you get it translated, it's just an equation that needs to be solved. So we're going to concentrate a lot on how to translate from this story or this application of math to a solution. So let's get started, and let's talk about some of the key things you have to do. First off, we're talking translation. So when you're translating something, you really need to be careful about the little tiny words, so that you don't translate them incorrectly. So you don't want to skim it, is what I'm trying to say. So you need to read it carefully, translate, maybe read it another time, check your translation, and then say, okay, that's what I'm translating it to. All right, so let's look at this first problem, and we're going to read it and decide what kind of problem we have, and then we're going to attack it and get it translated. So it says the sum of twice a number and 4 is 18. Find the number. So this is not one of those more complicated kinds where you're doing mixtures of percentages or distance, rate, and time. This one is truly just a straight translation. If we can just get from the English to the math, then we're almost done. That's the hardest part. So it's a strict translation, just solving for a number. Now, a lot of your teachers get really picky about this, and some don't care, but this is a good habit. So let's define what it is we're looking for. So it says find the number. So whatever it is we're finding, we're going to call that x. So let x equal the number. I could get this to write just a tiny bit better. The number. Now, we're going to go back and read the rest of the problem, and everywhere we see anything that talks about a number, the number, or just number, we're going to translate that to x, because we've already said x represents the number. So this says the sum of twice a number. Okay, twice a number is x. That's the translation into math for number. And 14 is 18. Okay, so sum means to add. Twice x is 2x. And we're going to add that to 4 is 18. Now let's read it one more time. Make sure. Sum of twice a number, and 4, okay, is 18. So if you're going to spend a lot of time somewhere on these problems, you spend it on the translation. I strongly encourage you that you have read this problem at least 3 times. Once to go, okay, I know how to do those. Second, to try your translation. Third, to prove it at least that many times, because if you're going to make an error, most likely it's in this first step. All right, so let's try this. So once I get to this part, then I don't care that it came from a story problem. And I go, oh, it's linear. It's got one variable. I want simplify my left, simplify my right-hand side, get my x's all isolated on one side, constants on the other, and then solve for x, get a 1x. So those same steps that we learned previously are going to keep going through here. So on the left, I can't add 4 to 2x, nothing to simplify on the right. I get my x's on one side, which means I want my constants on the other. So 2x would be equal to 14. Then I want to know what x is, not what twice x is. So the 2 is multiplying right now, and the opposite of to multiply is to divide. We always do the opposite of what it's doing, currently doing, to move it to the other side or to get rid of it. So like here, 4 was being added. The opposite of to add is to subtract. 2 is being multiplied. The opposite of to multiply is divide. We have x is 7. And I think that's my answer, but I'm just going to read one more time and try to put the 7 in there while I read it and see if that checks. So the sum of 2 times 7, because I think that's my number, and 4, is that 18? It's my little question mark. Is that 18? Yeah, 14 plus 4 is 18. So I feel like before the teacher gets to it, I have the right answer. All right, let's go over here and try another one. And this one says twice the sum of a number and 4 is 18. Now let's compare for just a second. See how this one says the sum of twice a number, and this one says twice the sum. Find the number. Okay, so again, we're going to compare and contrast here a second. We're going to let x be what we're trying to find. So what you're trying to find is x. Everywhere you see it, it's now going to be called x. So look at this one, and this one says twice a number. So it's 2 times a thing. Okay, it's twice a number, which is x. This is twice the sum. So this is 2 times a sum. Not 2 times a thing, 2 times a sum. So this is twice the sum of a number and 4. So this would be x plus 4 is 18. So I'm going to back this up. Look one more time. So if you look, this one over here, the first one, is twice a number. So here's 2 times x. This one is twice the sum. So here's 2 times the sum. So it's in parentheses. So do you see the difference? Okay, let's go ahead and get started. So can I simplify the left-hand side? Yes, I can. So 2 times x is 2x. 2 times 4 is 8. Is equal to 18. Can I simplify the right? No. All right, isolate my x's, so I'm going to leave them on the left. So I need to move the constants to the other side. What's the opposite of adding 8? To subtract 8. So 2x and 18 minus 8 is 10. Now I want to have just an x. So how do I negate, remove, or simplify it 2 times something? I do the opposite, which is to divide. So x is 5. And I think that's my number. So let's go back up here and read it kind of into the English. And it says twice the sum of a number and 9. Well, let's do this part first. The sum of a number, I said 9, and that's the answer. Okay, not the answer, but the part for the sum. Okay, so the sum of a number and 4 is 5 plus 4, which is 9. Right. And then we're going to double that and see if that's 18. And yes, it is. So I was thinking that in my head, and I spoiled. It's like spoiling a story and telling you the punchline first. But I hope you forgive me. Okay, let's do one more. I hope you're kind of getting the hang of this. All right. And we're going to do one of these where it's talking about the difference. Now, before we get started on this, I want to remind you of something. The ones that we did before were just sums or adding. So when you're adding something, 2 plus 3 is the same thing as 3 plus 2, right? It doesn't matter which way that you add them. And this would be like one of the properties, and they always have like the commutative property of addition or multiplication, but they don't have of subtraction because order does matter, or this, so 3, let's look at this again. 2 plus 3 is true, but 3 minus 2 is not equal to 2 minus 3, because this would be 1, and this is not equal to -1. So order matters when you're subtracting. It also matters when you're dividing, right? 3 divided by 2, which is 3 halves, is not the same thing as 2 divided by 3. So if they're talking about something that's subtraction or something that's dividing, then you have to be even more careful about your translation, because if you get them in the wrong order, then that first initial step for your translation is incorrect. So we have to be really careful about the order. So let's look at this next one. And it says the difference, so we need to be careful even more than normal. The difference of 3 times a number and 6 is 4 less than twice the number. Okay, now that's kind of a little bit step up. So we're going to try to find the number. So this is x. So let x equal the number. All right, everywhere we see number, we're going to write x. So this is x, and this is x. So now we have it in 2 places. This is actually your equals. So everything that comes before it is on the left side of the equals, and everything after is on the right. And let's be careful about this. So when it says difference, when it uses the word difference, then the way it mentions them after the word difference is the order that you write them down, right? So if it says the difference of 3 and 2, then it would be 3 minus 2. If it was the difference of 2 and 3, then it would be 2 minus 3. So when they use the word difference, the order that you're going to write them down in is the order that it's presented to you, right? Now, when they use less than, okay, if I, for instance, let's say you had some cookies and I had some cookies, and I said I had 4 less cookies than you, then I would take your number and subtract 4, right? Because I have 4 less than you, I start with you and subtract 4 because I have 4 less. So when they say less than, then you subtract from the thing that follows it, right? If I have four less cookies than you, I start with you and subtract back 4 to find mine, right? So let's set this up. And it says the difference. So I'm going to subtract. What am I going to subtract? The first thing they mention is 3 times x. And then the second thing they mention is this and 6. So we're going to subtract the 6, right? Because when they would use the word difference, we do them in that order. Is my equals. And if I'm going to say 4 less than twice x is 2x. And I have 4 less than that, so it's 2x minus 4, right? So read it again and look at what we wrote. The difference of, okay, here's my difference. The difference of 3 times a number, 3x, and 6, yeah, 3x minus 6 is, that's my equals, 4 less, here's my 4 less, than twice a number, than twice x. I think that looks pretty good, all right? Then you go, all right, here we go. So can I simplify the left-hand side? No, because I can't take 6 from 3x. Can I simplify the right-hand side? No. Can I get all my variables on one side? Sure, let's do that. Let's do it on the left. So we get rid of them on the right. It's adding 2x or positive 2x, so I subtract from both sides. So this would give me x. You can do these at the same time, but sometimes students don't want to do that, so I'm going with the more step approach rather than fewer steps, but feel free to leave this, combine 2 steps. Then I just want my x by itself, so the opposite of subtracting 6 is adding 6. So x is 2. And you should go back and check this and check it back up into the English and see if that makes sense. Okay? All right, let's do this one. Let's read this one. And it says the length of each side of a square is increased by 2 inches. The perimeter of the new larger square is 56 inches less than twice the original perimeter. What's the length of the side of the original square and the new square, which is the larger square? All right. Now this is not just to me, it is not just a strict translation of English into math. This is a geometry problem, and so there's most likely things that you have to know that from your past that you have to bring forward in order to get this problem straightened out and solved. And we're going to talk about the geometry words in here. But I also want to tell you that sometimes it really helps if you have a picture, if you can just draw some sort of a picture about the situation that's going on. It really helps to see. So let's read it again and go, okay, this is geometry problem. So let's go back and find what it is I'm doing. And it says the length of some square is increased by 2 inches and the perimeter, okay, what is the perimeter? The perimeter is when you go around and add all the sides, right? It's not an area where you're multiplying something, the length times the width, or 1/2 the base times the height. The perimeter is where you just go around and add up all the edges, right? Is 56 less than twice the original perimeter? What's the length of the side? Okay, so the original square, so let's start with the original square. So let x equal the length of the original square side. Because you remember that for a square, as opposed to a rectangle, right, let's draw. So a rectangle is normally not a square, even though a square is a subset of a rectangle. So a rectangle, can have like this could be 3, this could be 2, but a subset of a rectangle is if the two sides are equal. So if this was 2 and this was 2, then it would be a square. So the idea about a square is that all the sides are the same length. So on my original square, each side is x. And you may have called it s. It doesn't matter if you call it x or s. So that's my original square. All right. Then it says each side is increased by 2. Not quite a square, but you kind of get my drift. All right. Looks more like a rectangle. But there's my new square. All right. So what's the perimeter of the original square? So the perimeter of the original square is you would start somewhere. Let's say we started at this corner, and we're going to go around and add all these sides as we go. So we'd have the x on the bottom, the x on the right, the x on the top, and the x on the left. And you may have learned this in the past as 4 times whatever the length of one side is, because all the sides are equal. Doesn't matter how you get there, but the perimeter of the original square is 4x, right? So the perimeter of the second square, if you want to do it the same way, there's nothing wrong with that, is you would have the x plus 2 on the bottom, the x plus 2 on the right, the x plus 2 on the top, and the x plus 2 on the left. You can just go around and add all these up, or you could say it's 4 of the x plus 2's. You okay? All right. Now, let's look here. And so what have we done? The length of each side is increased by 2. Okay, checked, done that. The perimeter of the new larger square is 56 inches less than twice. Oh, this right here, this part right here, is my equation that I'm going to solve. And these are the answers that I have to give them. So this is the equation. All right. So the perimeter of the new larger square, okay, that would be this one right here. So the perimeter of the new larger square is, because this is my equals right here, 56 inches less than, so it's not a difference, it's something less than twice the original. Okay, so I start with twice the original, so it's 2 times 4x, which is the original, minus 56, right? The perimeter of the new larger square, okay, that's 4 times x plus 2, is 56 less than twice the original. Okay, I kind of think that's right. So simplify the left. You would go divide parentheses. Yes, can't add 2 to x. I don't have any exponents, but I could multiply. 2 times 4x is 8x. Okay, then I want to get my variables on one side, okay, and my constants on the other. Usually we put them on the left just because people get into a habit of doing that, but you can put them on the right. If I put them on the right this time, that's actually a benefit because I end up with a positive 4x. Otherwise, if I put them on the left, I'd have a negative 4x, which is just another step to do. All right, so I'd have 4x minus 56 equals 8. Then I want my 4x's by themselves, so I add 56, which is the opposite of subtracting 56. So 4x is equal to 64. Let's do it the other way so you can see it. 64 is 4x. And I want to know what x is, so I divide by 4. 4's cancel out to 1. And 4 goes into 64 16 times. Right? Now, what is x? Okay, x is the length of the original square, or which is one of the questions. Now, one of the things you have to be careful of is when you have geometry, if they give you units, you have to use units in your answer or you're a little bit wrong and they'll take points off. So x is 16 inches long, and that's the original square. And the new square side is 2 inches longer. So what you do is you take 16, put it in here where x is. So 16 plus 2 is 18 inches. So the newer square is 18 inches, and the smaller, older square is 16. And you can go back up in there and check it. But this is going to be a long video, so we're going to keep moving. All right, now we're going to talk about triangles. It's another geometry problem. And it says a triangle has 3 sides of unequal length. Okay, the middle length side is 5 more than the shortest, while the longest side is 3 times the shortest. If the perimeter is 65 centimeters, find the lengths of the 3 sides. Now, we need to give somebody a name, and somebody has to be like X, okay? Or you could use S for side or something. But we have 3 things, and so we need to figure out which one's going to be kind of like the original, the basic x. So watch here, the middle length side is 5 more than the shortest, while the longest is 3 times the shortest. So do you see how the other 2 sides are given to you in terms of the shortest? They're compared to the shortest. So the one that you compare to, that's the one you're going to start with. That's x. All right? So let x be the shortest side. So what you compare to is x. Right? So now, every time I see the shortest, okay, here's the shortest, this would be x. And here's the shortest, and this would be x. And let's read it again. And if you want to, we can write this out up here at the top just to help you a little bit. So it says the middle side is 5 more than x. Okay, so what's 5 more than x? X plus 5. And the longest side is 3 times x. What does that look like? 3x. So the shortest side is x. The middle length is 5 more than x. And the longest is 3 times x. And I think I've got those all down. And it says the perimeter is 65. Okay, so the perimeter says go around and add all the edges. Okay, so x plus 5 plus 3x equals 65. So can I simplify the left? Yes. 1x plus another x is 2x's plus 3x down here is 5x. So 5x plus 5 is 65. I isolate my variables on one side. So I want to get rid of the minus. I need to get rid of the 5 by subtracting 5, so I have a minus 5. So 5x is equal to 60. Divide both sides by 5. And x is 12. Don't forget your units. And the short version for centimeters, rather than to write that all out, is cm for centimeters. That's the abbreviation. And then we remember we had the middle side was x plus 5. So if x is 12, 12 plus 5 is 17. And the longest side was 3 times x. So you don't put 17 in there, you put the 12 in here. And so this would be 3 times 12 is 36. All right? Don't know that you want to leave on your teacher's grade that they're going to grade, where you draw little lines like that. You may not need to draw them. Now, just to check it, since this isn't so bad, let's add these up. Does this add up to 65? Yes, it does. All right. Let's look at this one. And it says, Joanna sometimes uses her car to get to work and sometimes uses a bicycle. When she bicycles, it takes 50 minutes to get to work. When she drives, it takes 30 minutes to get to work. Her average driving speed is 10 miles per hour greater than her average bicycling speed, which makes you wonder how slow the traffic is there, isn't it? Anyway, how far does she travel to get to work? Now, this one, so why I want you to read it through first is to kind of get your head, into this game about, okay, what kind of problem is this? So it's not just a straight translation where I just call it X and then read it very carefully and write it down. It's not a geometry problem where it's going to require me to do areas or perimeters or, maybe draw a figure. This one has to do with how much speed somebody has when they're traveling. This could be airplanes, this could be swimming, this could be people walking, this could be like here, automobiles or bicycles. So once they start talking about somebody's speed, okay, where it's like 10 miles per hour is greater than, and they talk about distances, that sort of information. So once they start talking about those, which this is a very common problem, these are almost always centered around this distance is equal to rate times time. So the distance that you travel is equal to your rate, how fast you're moving, your speed, times the time that you're doing that. So if you were driving 50 miles per hour and you did that for 2 hours, then, and you didn't slack off or anything, but if you're out on the highway driving, well, I guess you'd be faster, but let's just stick with 50 miles per hour for 2 hours, you would have traveled 100 miles, right? Okay, so it often helps to make like a little chart, okay? So what we would have is we've got a bicycle and we've got a car. And we've got the distance they're going to travel. And we've got the rate. And we've got the time. So we're going to make little columns for this. And we're going to fill in what we know. All right. Now, it says she uses her car, right, get to work, and sometimes uses a bicycle. Actually, this kind of information is like, okay, it makes you see a story, but it's totally irrelevant to the math, right? When she bicycles, it takes 50 minutes to get to work. Okay, so when she bicycles, it takes 50 minutes. So the time here is 50 minutes. But keep in mind, this is 10 miles per hour, not 10 miles per minute. Okay, so we're going to end up with miles per hour. So don't be mixing minutes in with hours. So if it's 50 minutes, how much of an hour is that? Okay, isn't 50 minutes, okay, compared to 60 minutes, isn't that 5/6 of an hour, right? So this is 5/6 of an hour. That's the time. Okay. Then when she drives, it takes 30 minutes. So 30 minutes out of the 60 minutes for an hour is half an hour. So this is 30 minutes, but it's a half an hour. All right. And then we need to talk about the rate. And the rate is how quickly you're moving, your speed. So what does it say here? So now we've taken care of this one, and we've taken care of this one, and her driving speed is 10 miles an hour greater than her average bicycling speed. So they are comparing driving to bicycling. They're not telling you she's going 20 miles per hour or 50 miles per hour or whatever. They're saying her average driving speed is 10 miles per hour greater than her average bicycling speed. Okay, now it doesn't say 10 miles per hour times, okay, or 10 times her average speed. It's saying 10 miles per hour greater. Greater than means to add. All right? So this part that they're comparing to is x. If I compare it to the bicycling speed or rate, that is x. And the driving speed is 10 miles per hour greater than that. Okay, so it'd be x plus 10. And since she's traveling either way to get to work, these two distances are equal. Right? The distance that she's going to travel by bicycle and the distance she's going to travel by car are the same. So the distance by bicycle equals the distance for the car. This is actually going to be your equation. Now, how do I get that using this? Well, the distance of the bicycle is the rate of the bicycle times the time of the bicycle. And the distance of the car is the rate of the car. Let me spell that out. Times the time of the car. So we sort of had to translate again. So what's the rate of the bicycle? X. What's the time? 5/6 of an hour. What's the rate of the car? X plus 10. What's the time? A half. So this, I'm going to switch around so it looks a little bit better. 5/6x equals 1/2 x plus 10. I don't know about you, but having fractions at the end is kind of like, just sets my nerves on end. Okay, and whatever you can do to kind of reduce the hair on the back of your head standing up, that sort of helps. So I don't care for fractions, so I'm going to use one of the things we learned about simplifying is to clear what they call clear the fractions, which means let's get rid of the fractions and just have it look like integers. So you would find the least common denominator. Remember this from the simplification video. You would find the least common denominator and you would multiply both sides by that. So the least common denominator between 6 and 2 is 6. We're going to multiply both sides by 6. So this 6 cancels this 6, and I just have 5x. That's what they mean by clearing the fractions. You're getting rid of the fractions and having just what looks like a more comforting equation with just integers. Now be careful here. When you multiply, this 6 just multiplies the 1/2. It's not going to come down here and multiply what's in the parentheses because the distributive property only works when you have a number right next to this parentheses with the addition. It multiplies across the addition. And there's no addition right in here. It's just a straight multiplication. For instance, if you had 2 times 3 times 4, you go 2 times 3 is 6 times 4 is 24, right? You don't go 2 times 3 and 2 times 4. You just go 2 times 3 is 6, 6 times 4 is 24. So that's just the same as over here. So 6 times a half, this 2 goes into here 3 times, and I have 3 times x plus 10. So I can still clean up a little bit on the right. So now I could do the distributive property. So 3 times x is 3x. 3 times 10 is 30. So when my x is on one side, my number's on the other. Let's go back to putting them on the left. So 2x is equal to 30. I want to know what x is, so I divide both sides by 2. So x is 15. Don't forget your units. So what is this? X is 15. This is how fast she's bicycling. Okay. And then we had set up here that x plus 10 is the rate of the car. So x plus 10, well, 15 plus 10 is 25 miles per hour for the car. Okay. Still hanging in there? All right. Let's do another one. This is also a very popular kind. And it says 2 cars are traveling in opposite directions. One's traveling at a rate of 40 miles per hour, the other at 50 miles per hour. They leave from the same point at the same time. How many hours will it take for them to be 600 miles apart? And you're going, okay, so this is one of those. This isn't a geometry problem. It's not really a straight translation. It kind of is. But this is one of those distance equals rate times time, because they've talked about the rate, the speed. They've talked about distances. This is one of those distances. It's equal to rate times time. So we have car 1 and car 2. And we've got distance, rate, and time. All right. I could try to make those a little bit better straight. It is, well, mine's straight and slanted. Okay. I don't know if that's an improvement or not. So let's see what it is that we know. All right. 2 cars are traveling in opposite directions. So we've got, and they leave at the same spot. So we've got, let's say, car 1 goes this way, car 2 goes this way. One is traveling at the rate of 40 miles per hour. All right, so let's just say this one's 40, because it doesn't really specify which one's which, and this one's 50. All right. They leave from the same point at the same time. How many hours will it take for them to be 600 miles apart? So in this case, they're looking for a specific time. Let's go ahead and just call that T. Okay. So how long is car 1 traveling? The same amount of time that car 2 is traveling. Right. Now, does it say anything about distance? It kind of does, doesn't it? This total, the distance total, is 600 miles, right? Okay. So the distance of car 1 plus the distance of car 2 equals 600, right? Now, distance is equal to rate times time, right? So the distance of car 1, its rate is 40, and its time is some amount of time t. What's the distance of car 2? Its rate, which is 50 miles an hour, times its time, which is the same amount of time as, because they're just driving for the same amount of time. And this is 600. Right? So simplify the left, simplify the right, get your variables on one side, which they are. Okay, constants on the other, which is they are. Okay, now we're going to get a 1x if you called it x or t. So t, and when you divide this out, this turns out to be 6 2/3 hours because it said how long is it going to take. Now, this is fine, 6 and 2/3 hours. But if they want to know how many hours and minutes this is not 6 hours and 2/3 of a minute. Okay? This is 6 hours and 2/3 of another hour. I want you to be clear about that because sometimes they ask you. So this would be 2/3 of an hour, which is 60 minutes. Okay, so this is 6 hours, and 3 goes into 60 20 times, and 2 times 20 is 40 minutes. So if they want hours and minutes, please be careful with that conversion. All right, this is the last type, okay, for this part of story problems for this video series. These are what I call mixture problems. A lot of books call them mixture problems. And it says one container has 20 ounces of 10% saline solution and a second container has 40 ounces of 5% saline solution. How much 5% solution needs to be added to the 10% solution to get 7% solution? How many ounces of 7% solution will you have when you get done? You know, this reminds me of stuff that was going on during COVID when you had alcohol, right? And you were trying to find alcohol so that you could clean things, you know, in the early days when we were just trying to get a handle on how to treat this. And oftentimes after everybody bought stuff up, you couldn't get the exact percentage you needed. You know, maybe you found a special deal on 90% alcohol and you really only needed to get 70%. So this is something you might have to do, you know, in real life. All right. So let's try to practice this. But this also has a certain format, you know, just like distance problems seem to have and work well with this chart where you're talking about distance is equal to rate times time. So you keep this in mind. You construct a little chart and then work your way through it. This also has a pattern for these mixture problems. And so what works is that you're going to have a percent, okay, of some type 1 and an amount of type 1. And there's a times here. Okay, the percent of type 1 times the amount of type 1 plus the percent of type 2 times the amount of type 2 equals the final percent times the final amount after you mix them together. Okay, so it's kind of like percent times amount plus percent times amount equals the final percent times amount. So I'm taking out the subscripts so that you can kind of see that it's a percent times an amount. All right, now here we go. Alrighty, and it says, let's see what we've got. One container has 20 ounces of 10% saline solution, and a second has 40 ounces of 5. How much 5% needs to be added to the 10% to get 7%? All right, now there's a lot of kind of implied information in here. So what's implied is you have this container, okay, with 10% solution. I always feel like I'm in a lab, you know, with some beakers going to pour things into each other. All right, so I have a container that has 20 ounces of 10%. And I'm going to pour into it, okay, 5%, and I'm going to dilute it down to 7%. Okay, so I got this big container. I've got 10% in there. I'm going to pour 5% in. Okay, so what's my type 1? I have 10%. Now, how do we do percent in problems? 10%. When you put them in a problem, you don't use the percent sign. You want a decimal. So to change a percentage to a decimal, you move away from the percent sign and you move 2 decimal places. So you start right here, move 2 over, Because the reason it's 2 is it's per cent, which is per 100, because cent is short. Like century is 100 years, right? 100 pennies and a dollar. So this is per cent per 100, right? So how many decimal places do you have to get to 100? 2. Okay. So we're going to move here. So go 1, 2. So this is 0.1. If you had 20%, you would move 2 places, drop the percent. If you have 5%, you would move 2 places, filling in with a 0, and have 0.05. All right? So we have to change from the actual percent sign to a decimal. So 10%, we're going to move 2 places to the left and drop the percent. This is 0.1. So 0.1, right? What's my amount? 20 ounces plus, all right? Now my next percentage is 5%, and 5%, we move 2 places. It's 0.05, so it's 0.05. Okay, how much am I going to use? So I've got 20 ounces of 10%. I'm going to pour the 5% solution in. How many ounces do I need? I don't know. That's the question. So how much 5% needs to be added? That's X. Okay. Okay. Equals my final percent. Now, what's my final percent? I want to get 7%. So I have 7%. I need to change it to a decimal. I move 2 places over and drop the percent sign. So this is 0.07. That's my final percent times my final amount. Okay. Now remember, we had 20 ounces, right? We're going to pour X ounces in on top of it. How much do I have together? Oh, no. Okay. I have my original 20 plus whatever X I poured in, right? So does it make sense? So this is, I have 10%, 20 ounces. I add in 5%. I don't know how many ounces. That's what I'm going to figure out, because I want 7% of some total after they're both in the beaker. Okay. So here we go. All right. So here we go. 0.1 times 2, 20 is 2. I keep giving you the answer before I actually write it down. 0.1 times 20 is 2, right? 0.05 times x is 0.05x equals 0.07 times 20 would be 1.4, and 0.07 times x is 0.07x. Now I want my x's on one side, my numbers on the other. So I always try to put my x's on the side that leaves it positive. So since I have 0.07 over here that's larger than 0.05, I'm going to subtract 0.05 from here and subtract it over here. So I have 2 plus, well, I erased those because these are going to cancel. So I have just equals 1.4. And 0.07 minus 0.05 is 0.02. If I've got my variables on the right, I don't want the constants with it, so I subtract 1.4 from both sides. So 0.02x is 0.6. I want to know what x is, so I divide both sides by 0.02. And when you divide that out, you get 30. Okay, now what does that mean? X is what you're pouring in, so you need 30 ounces of the 5% solution, right? Now remember, we started out with 20 ounces, right? And the question says, How much 5% solution needs to be added? Okay, I did that. Okay, I have to add 30 ounces. How many ounces of the 7% will you then have? Okay, well, I started off with 20, right? So the total amount is the original 20 ounces that I had. I should space that over there. Plus the new 30 ounces. So the total amount is 50. There you go. Doing all right still? I hope so. All right. One more. One more. We're almost done. Okay. A 50-pound sack of animal feed is 30% oats. How many pounds of pure oats must be added to the feed mix to have a mixture that is 60% oats? Alrighty. So how many pounds of pure oats? That's the question. Let's let X be the number of pounds of pure oats. Now, what does that mean? It's just straight oats. There's nothing mixed in with it. All right. So remember, we go percent times the amount plus percent times the amount equals the final percent times the final amount, right? So we're trying to change the percentage of oats. So that's what's going on right here. So we start off with a 50-pound sack, and it has 30% oats. What does 30% look like as a decimal? So 30%, you move the decimal 2 places to the left and drop the percentage sign. So this would be 0.3. Okay. What does 60% look like as a decimal? You have 60%, you move 2 places to the left, and you drop the percentage sign. So this is 0.6, right? So we have percent times the amount for type 1 plus the percent times the amount for type 2 equals the percent times the amount of the final. AMT is short for amount, right? Percent. Now, so here we go. So what did I start off with? I had percent, which is 0.3, because even though we write percent, we want it as a decimal, right? So 0.3, which is 30%, times 50 pounds. That's my percent times my original amount plus. Now, this is where it gets kind of crazy, okay? What's the percentage if it's pure? Okay, if it's only oats, all of it is oats, not 60% oats, not 50% oats, not 40% oats, but 100% of it is oats, right? How many pounds of pure oats? So it's 100% oats, all right? So how do I get it into decimal form? You start right here. You move the decimal 2 places back. You have 1.0. You drop the percentage. Well, 1.0 is just 1. So something that's 100% whatever, 100% oats, 100% saline, 100% chocolate, okay, whatever it is that's 100% or pure, then that's 1. Okay, so here's my percentage. This doesn't look like a percentage. This is percentage as a decimal, but this is going to be 100% of, I don't know, so many pounds of the pure oats, okay, equals the final percent, and the final percent I want is 60%, which looks up as a decimal as 0.6, times the final amount. Okay, well, what's my final amount? Well, I started off with 50-pound sack, and I'm going to add in X pounds, right? So it's 50 plus X. So look over your equation. 30%, 0.3 times the initial amount, 50, plus what I'm going to add in, 100%, which is 1, times some unknown amount, which is X, equals 60%, 0.6, times the total amount I end up with, 50 plus X. Okay, that seems like that's on the right track. So let's get busy. So 0.3 times 50 is 1.5 plus, well, 1 times X is X equals 0.6 times 50 is 30, and 0.6 times X is 0.6X. So 1x is bigger than 0.6x, so I'm going to move my x's over there so they're positive, because I just like that. When I work with a negative number, sometimes it's just one more thing to keep up with, and sometimes I get it lost, okay? I don't know if you ever lose that, but okay. Now, this is understood to be 1, so 1 minus 0.6 is 0.4. All right. And then this should be 1.5. It should be 15. Sorry about that. I hope you caught that. All right. So I got busy talking and went, okay, how did I end up with 1.5? So this should be 15. I beg your pardon. All right. So this should be 15. So then we subtract 15 from both sides. And 0.4x is equal to 15. So I divide both sides by 0.4. So x is 37.5 pounds. So let's see if that works just for grunts. Okay. So technically what I'm doing, if you go back up into here, is I have 0.3 times 50, right? And then 1 times 37.5 pounds of pure oats. Does that equal to 0.6 of 50 plus 37.5? And if you check it, it does. All right. So what was my question? Let's go back up here and check. How many pounds of pure oats must be added to the mixture? 37.5. If they had asked you how many pounds of total feed now have you got, so you can see how long it's going to last, okay, then if they wanted the total, you would have your 50 plus your 37.5, and this would be 87.5 pounds if they wanted to know, okay, how many pounds of feed do you have now? Okay, so I hope that helps. I hope this helps you to be a little bit more confident when you're working through your problems. You have to go really slow, all right? And I've noticed that a lot of students, when they have to slow down and do this, they don't want to. I don't know whether it's because the story problems just make them kind of anxious, and so they want to get through it as fast as possible, or if they think that it's a comment on how quickly their brain works if they're going really slow. But I'm telling you, you need to go really slowly through these story problems, because if you're going to lose points between here and here is where the majority of the points get lost. Most people can handle it between here and here because you've been doing that for a while. It's not too bad. All right. But this part right here, if this was like a 10-point problem, 5 or 6 points of it is just going to be getting from here to here. So more than half the points are just getting that first line down. So please slow down. Please don't think of it as any sort of a commentary on anything other than you want to be careful and you want to score as many points as you can. So slow down and read it 2 or 3 or 4 times, all right? Okay, so that's it for this video. Don't forget that in the description, there'll be a link to some more practice problems for you to um, play with these and see how you're doing, and then a link to the next video. So see you at the next video.